Okay, so in last class we have studied about the distinction between crystalline materials and non-crystalline materials, and also we have studied allotropy and polymorphism, and also we have studied uh, the classification of crystalline materials like single crystal and polycrystal. Can you see the screen?
Yes, sir.
Okay. And also we have studied space lattice and basis, and also we have studied unit cell. Okay. We have studied unit cell, and then classification of the unit cell, primitive cell and non-primitive cell. And then we have studied lattice parameter of a unit cell in 3D. We have studied lattice parameter of a unit cell in 3D. Okay. Like is A, B, C, alpha, beta, and gamma. That was lattice parameter of a unit cell in 3D. And then lattice parameter of a unit cell in 2D is this one, A, B, and angle between them, phi. And there are 5 types of space lattices that we have studied. These are oblique lattice, square lattice, rectangular lattice, center rectangular lattice, and then hexagonal lattice. Okay, so we are going to study today the crystal systems. So if we analyze all the crystalline materials, we'll see there are 14 different types of Bravais lattices or space lattices are available. And these 14 Bravais lattices in 3D, of course, and these 14 Bravais lattices can be grouped into 7 different crystal systems. So that means we have 7 different sets of A, B, C, and alpha, beta, gamma. And within them, there are 14 types of Bravais lattices there. Today, we are going to discuss about this thing. Okay. So we are going to study all possible 3D space lattices. So as I mentioned earlier, there are 14 different types of Bravais lattices are there in 3D, and these among them, like 2D, there is one general. That means one general means there is no restriction in lattice parameters. That means it can be any A, any B, any C, or there is no restriction in interfacial angles as well. And there are 13 special. So that means some sort of restriction will be imposed in these cases. And these 14 Bravais lattices are conveniently grouped into 7 different crystal systems. So you should remember that thing. So we have 7 different crystal systems. These are triclinic, monoclinic, orthorhombic, tetragonal, cubic, trigonal, rhomboidal, and then hexagonal. So triclinic is a general one. And there is only one space lattices are there, and the relationship between primitives and interfacial angles are A is not equal to B is not equal to C. So you should remember that thing. And alpha is not equal to beta is not equal to gamma and is not equal to 90 degree. Nothing are 90 degrees. So this is the first space lattice and first crystal system. In this crystal system, there is only one space that is available, and the unit cell. So please try to draw the unit cell. Unit cell is this one. This one is the triclinic unit cell. And then monoclinic. In the monoclinic, the relationship between the primitives and lattice parameters are A is not equal to B is not equal to C, same as before. However, in this case, 2 angles are same. Alpha equal to beta equal to 90 degree, but gamma is not equal. And there are 2 types of space lattices are available. One is called simple. Simple means when the atoms are located only at the corner. When the atoms are located only at the corner, we call it simple. We call it simple. So previously the atoms are located only at the corner. In this case, we have simple monoclinic like this one. Okay, simple monoclinic. Atoms are located at the corner. The conditions are A is not equal to B is not equal to C, but alpha equal to beta equal to 90 degree and gamma is not equal. So this is simple. and then another base-centered monoclinic is there. Base-centered monoclinic in addition to the corner atoms. Remember, in addition to the, so please try to draw this unit cell. So in the exam, sometime I may ask you to draw the unit. So in addition to the corner atom, there will be other atoms at the center of the bases. So this is the base of this unit cell, and this is the base of the another unit cell on its top. So in addition to the corner atom, there will be atoms at the center of the bases. It's called base-centered monoclinic. And then number 3 is orthorhombic. In case of orthorhombic, as before, the primitives are not equal. However, the 3 angles are equal and they are 90 degrees. And in this case, maximum number of space lattices are available. These are simple. Simple means this one, atoms will be located at the corner. Look, atoms will be located at the corner only. And then base-centered orthorhombic. So we have described this one. Atoms will be located at the corner and also center of the bases. And then this one is new. It's called body-centered orthorhombic. Please spell it out. Body-centered orthorhombic. And another one is face-centered orthorhombic. Body-centered orthorhombic. This is the new unit cell. So body-centered orthorhombic is there will be atoms at the corner. So atoms at the corner will be always there. Otherwise, this will not be the unit cell. And then if we draw the longest diagonal in the unit cell is, there is one diagonal like this face diagonal is root 2a. And then with root 2a, like this one is root 2a, this one is root 2a, and with root 2a, there is another a is Pythagoras. So this distance will be root 3a. This distance will also be root 3a. And then they intersect here. So another atom will be located at the body-centered position. So this is called body-centered orthorhombic. And then in face-centered orthorhombic, atoms will be located at the corner, as it is always that will be at the corner. And in addition to the corner atoms will also be located at the center of every faces. As you know, this unit cell, this 3D unit cell has got 6 faces. So in addition to the corner atoms will be located at the center of the every faces. And this is called face-centered orthorhombic. So we have already covered 7, half of the space lattices. And the next one is, you see, at first nothing was equal, and then nothing is equal, and then in the next case, in monoclinic, 2 angles are equal. In orthorhombic, 3 angles are equal. Now, in tetragonal, in case of tetragonal, 3 angles are equal and 90 degrees, and A is equal to B but not equal to C. And there are 2 types of space, that is, one is simple tetragonal, so that means atoms will be located at the corner, this one, and then body-centered atoms will be located at the corner and also in the body-centered position. Okay, so that is called body-centered tetragonal. Okay, and then the easiest one, which is cubic. In case of cubic, A equal to B equal to C, alpha equal to beta equal to gamma equal to negative. All are equal. And then there are 3 space lattices in this case. These are simple, that means atoms will be located at the corner. And then BCCs, please spell it out. BCC means body-centered cubic. BCC. So this is the simple unit cell. This is the body-centered cubic unit cell, and then face-centered cubic. This is the face-centered unit cell. Atoms will be located at the corner and also center of the every faces. Okay, and then trigonal or rhombohedral. There is only 1 space lattices. That means atoms will be located only at the corner, and this is the typical unit cell. In this case, A equal to B equal to C, alpha equal to beta equal to gamma, but they are not 90 degrees. So that means, look, it is tilted. So this sort of materials is actually grown in case of thin film. When the thin film is grown on a substrate, if the lattice parameter of the substrate and the lattice parameter of the material that is grown on the substrate are not equal, then at the interface region, this sort of unit cells is grown over there. And as you can see, this is actually highly, it is this is already stressed. That means its energy is higher. Okay? So if you make some device using these materials, as it is already energized, so to excite it, it needs less energy. So it has got some advantage. Okay, and then finally hexagonal. In case of hexagonal crystal, atoms are, look, this is the top face, this is the top face, and there will be an atom here, and then bottom face, and also here. There will be midplane. There will be another 3 atoms in the alternative phases. Look, there are 3 tetragonal unit cells at the body center position. It will be at the body center position of each unit cell. Another layer will be there. Okay, we are going to discuss hexagonal prospect crystal structure later on as well. So that's all. So here is 14 different types of space lattices are available, and these 14 space lattices can be grouped into 7 different crystal systems. These are triclinic, monoclinic, orthorhombic, tetragonal, cubic, trigonal, and then hexagonal. We have to describe. Among them, if you look at if you concentrate orthorhombic and cubic crystal system, that contains half of the space lattices. And if we investigate the materials, we'll see most of the materials forms cubic, because cubic is the easiest one. And okay, so from now on, we're gonna concentrate, and as most of the materials form cubic crystal structure, and cubic crystal structure is the easiest one. So from now on, we're gonna study. We'll concentrate cubic crystal structure in detail. Now, from the crystallograph data, we can calculate atomic radius. We can estimate atomic radius, or if we know the atomic radius, we can estimate lattice constant. So, as we have discussed, cubic crystal system has got 3 different space lattices. One of the space lattices is simple cubic. So atoms will be located at the corner only. So this is the typical unit cell of simple cubic crystal. If we look at closely, this is the schematic diagram of a simple cubic unit cell. If we look at closely, one of the faces will be look like that. As you can see, if the materials are in pure form, so atom, if we assume that the atoms are spherical in shape, so this is called hard sphere model. That means we are considering atoms are hard, and also atoms are hard, and atoms are spherical in shape. If we assume that one, then this distance, this center to center distance, is actually A. This one is A, or this one is A. This one is A, this one is A, or this one is A. Now in this A, you can see here is one radius, another is one radius. Okay, or among them, atoms are located here, atoms are located there. And also, if you consider this one as a reference, atoms are also located over there. However, this distance is larger. So that is the nearest neighbor distance. This is the nearest neighbor distance. So atomic radius can be defined as half of the nearest neighbor distance. So if they are touching, okay, or in the hard sphere model, is the nearest neighbor distance, and half of that nearest neighbor distance can be termed as atomic radius. So the atomic radius can be defined as half of the distance between the nearest neighbor in a crystal of a pure element. You should remember that the material has to be pure. If it is not pure, then another different atom will be located here. Then you cannot calculate properly the atomic radius in this case. So in case of simple cubic crystal, atomic radius A equal to 2R. Okay. So here R is the half of the lattice constant. That means R equal to A by 2 in this case. We are going to do the same thing. We are going to find out R in terms of lattice constant for other space lattices in cubic crystals. And other space lattices in cubic crystal systems are body-centered cubic and face-centered cubic. To do that, simple cubic crystal is so simple that among the element, only polonium, there is one material named in honor of Marie Curie, according to her birthplace, Poland. So it's called polonium, and polonium has got this sort of question. If you look at the 3D view of a unit cell, it will look like that. Okay, and if we draw, this is very important one. If we draw several unit cells side by side, and if we take this one as a reference, so these the atoms located in the shaded atoms, located at a distance A, which is the nearest neighbor distance in this case. So how many atoms are there? 6 atoms. These 6 atoms are called nearest neighbor. Okay, later on, we will see, we will call this one as coordination number. And coordination number is very important for a material because the property of the material depends on coordination number. Why the property of the material depends on coordination number? You can understand it very easily. Suppose we inject some electron in the material. So when this atom gets extra electron, so if there is if there is no empty electronic states here, so it will try to disperse those electrons. So and that electron will disperse through this nearest neighbor distance. If the number of nearest neighbor is higher, so it can pass the electron very easily. That means that materials will be less resistive. Okay, and if the nearest neighbor number is less, it will be more resistive. So I just give a very simple example. Similarly, other property of the material also depends on nearest neighbor number. Okay. Now, body-centered cubic crystal. So these are the atom stack of the atom of a body-centered cubic crystal, and if you look at very closely, it will be this one. Only one unit cell. If I ask you to draw the typical unit cell of a body-centered cubic crystal or schematic diagram, this will be the answer, the easiest one. So atoms will be located at the corner, and also atoms will be located at the body-centered positions. So as before, the atomic radius is defined as half of the distance between the nearest neighbor. So we should look for nearest neighbor distance. So in this case, if we take this one as a reference, atoms are located at distance A, and also atoms are located at distance root 2A. Atoms are located at distance root 3A, and also atoms are located over here. That means at a distance root 3A by 2. Now you see that this root 3A by 2 is less than A, and A is less than root 2A, and also that is less than root 3A. That means root 3A by 2 is the nearest neighbor distance. So to find a nearest neighbor distance, so half of this root 3 by 2 is called, half of this root 3 by 2 is called atomic radius. So atomic radius is half into root 3 by 2, that means root 3 by 4. That's the atomic radius. Or if you look at here, among this root 3a, one radius from that corner, another radius from that corner, and also the diameter of the middle body center atom. That means R, twice R, and then another R. That means 4R makes root over 3A. 4R equal to root over 3A. So R will be root 3A. It's very easy to understand. Now the materials like chromium, you should remember that thing. I might ask you what is the crystalline nature of chromium. So answer will be body centered cubic, chromium, and then alpha iron, molybdenum, lithium, tungsten, titanium, tantalum have this sort of structure. So in the exam, I might ask you what is the crystalline nature of tantalum. So answer will be crystalline nature of tantalum is body centered cubic. If I ask you to draw a typical unit cell, you will draw this unit cell. And then if I ask you to find out the expression for the atomic radius, so you will derive this relationship. So that's the answer. Next topic is face-centered cubic crystal. So in case of face-centered cubic crystals, these are the atomic stack. Okay, atoms are located at the corner and also in the face-centered position. Although we indicate the face-centered atom in white, actually these to become face-centered cubic, this face-centered atom has to be the same atom. We just change the color to identify the face-centered position. However, these atoms are exactly the same atom. If these are not the same atoms, you cannot term this one as a face-centered cubic. And if you look at very closely, the only one unit cell, it will look like that. And if I ask you to draw a typical unit cell for face-centered cubic crystal, answer will be this one, because the atoms are located at the corner. So this C will be here, here. So atoms will be located at the corner and also in the face-centered position, like this one. Atoms are located over here. Now, as before, to find out the expression for the atomic radius, we will calculate half of the, at first we will calculate nearest neighbor distance, and then we divide that one by 2, so that will give you the atomic radius. Okay, so now, which materials forms face-centered cubic crystal? That's a very important question. We'll see the materials that is useful for our daily life. All has got the, almost all of them has got the face-centered cubic crystal structure. So like materials like copper, very important materials for our life, aluminum, copper, aluminum, silver, gold, nickel, platinum, lead, sodium chloride, calcium have got this sort of crystal structure. And also there is another form of iron, which is, you know, the iron is allotropic. Gamma iron is also face-centered cubic. Okay, so now as I said, I'm going to find out the nearest neighbor distance. So atoms are located at a distance A here, at a distance A there, at a distance A there. Also, atoms are located at a distance root 2A, this one. And atoms are located at a distance root 2A by 2 as well. If you calculate this one, root 2A by 2, root 2A by 2 actually less than A. It's less than root 2A, of course. So root 2A by 2 is the nearest neighbor distance. And half of root 2A by 2 is atomic radius. So atomic radius will be root 2A by 4. Or if you look at this AC distance is root over 2a. Why this is root over 2a? Because this distance is a, this distance is also a, so this will be root 2a. And among this root 2a, you have one radius and then two radii, the diameter, and also another radius. So 4 radii makes root 2a. So one radius will be root 2a by 4. That's the answer. So we have derived the relationship between atomic radius and lattice constant for various space lattices in cubic crystal systems. In cubic crystal system, there are three different space lattices. These are simple cubic, body-centered cubic, and also face-centered cubic. And we have seen that in case of simple cubic, R equal to A by 2 in case of simple cubic, and in case of body-centered cubic, R equal to root 3 A by 4, and in case of FCC, present case, R equal to root 2A by 4. That's very important. And also we get some examples of simple cubic, body-centered cubic, and also the face-centered cubic crystal. So this is a typical unit cell for simple cubic crystal, and this is the typical unit cell for face-centered cubic crystal. Okay. Now, how we shall grow the FCC crystal? We'll see this one. You see, if you, as we have considered that atoms are spheric, hard and spherical in shape. If atoms are hard and spherical in shape, so you can, if you arrange the atoms, then you can place, look, if this one, you can arrange 1, 2, 3, 4, 5, 6 atom maximum, surrounding that one, okay? You cannot place more than that. So, so this is this one. This is the nearest neighbor. This is the nearest neighbor. Nearest neighbor. You can place 6 atoms. Okay. So this is the first layer. This is the first layer. Now, if you place the second layer, touching 3 atoms of the bottom layer, like this one, 3 atoms of the bottom layer, and this already touched, so another 3 atoms will be here. This already touched, another 3 atoms will be there. So in the second layer, if you place, this is the second layer, okay, and then if you place the third layer, so look, these are the positions touching the three atoms. So it's the position C, another position is C there, and C position is the third layer, okay. So if you arrange the atoms, first layer touching 6 atoms, and the second layer touching place in atoms touching 3 atoms at the bottom layer, okay, and also in the third level you place the atoms in position C, and then again A, B, C. If you arrange them in A, B, C stacking sequence, so that will form the face-centered cubic crystal. And if you just arrange A layer and then B layer I said middle, B layer, A, B, and then A. This A, B, A will form the hexagonal crystal structure, which we will study later on. So look, so this is the first layer, and then this is the second layer touching field, and this is the third layer. And if you look at the 2D projection, this is the 2D projection, and 3D atom, 3D arrangement of the atoms will look like that. So this is the construction of a face-centered. Face-centered. If the atoms are arranged in such a manner, we call it face-centered cubic crystal. And if the stacking sequence is AB, AB, C is not there, AB, AB, then we call it hexagonal close-packed crystal structure. Okay. Now we are going to find out number of atoms per unit cell in various space lattices in cubic crystal systems. So how many space lattices in cubic crystal system? In cubic crystal system, number of space lattices are 3 space lattices. Simple cubic, as we have studied earlier, body centered cubic, this one, and face centered cubic. So this is the typical unit cell. This is the typical unit cell. This is the typical unit cell. Now our task is to find out the number of atoms per unit cell. So this is a little bit tricky. This is the choice of unit cell is arbitrary. We choose the unit cell. So when you draw the unit cell, in normal vision, it will appear to you that the number of atoms is 8. 1 to 8 corners, 8. Actually, this is not the case because each corner atom is shared by other unit cell as well. Okay, so each corner atom basically shared by how many unit cell? So if you draw, this is number 1 unit cell, okay, number 2, and then number 3, and then number 4 unit cell in its own plane, and there will be another 4 on the upper plane. So altogether, each corner atom is shared by 8 unit cell. So contribution of this atom in this unit cell is 1 by 8. And as we know, the space lattice has got the identical position. So all 8 atoms will have got the similar status. So number of atoms in this case is 1 by 8 multiplied by 8 is 1. So number of atoms per unit cell in case of simple cubic crystal is basically 1. So answer is 1. Although it appears that the number of atoms is 8. However, if you consider the sharing case, which you have to consider, number of atoms will be 1. Now, we will calculate number of atoms in case of BCC crystal. In case of BCC, you have corner atoms and then body center atom. So corner atom is the calculation of the corner atom, contribution of the corner atom is as with the simple cubic. From the corner, so you will get 1 atom. And then this body center atom fully lies inside this unit cell. This unit cell is not shared by, this atom is not shared by other unit cell. So number of atoms in case of BCC will be this 1 plus 1 equal to 2. Now, if we do the same thing for face-centered cubic crystal, so you have obviously you have corner atoms. From the corner, contribution of the corner is 1, and this face-center atom is shared by, face-center atom is shared by, like this face-center atom is shared by this unit cell and other unit cell from here. Okay, this unit cell and the neighboring unit cell. So contribution of this atom is basically half. And then how many such faces are there? 1, 2, 3, 4, 5, and then 6. This one. 1, 2, 3, 4, 5, 6. So 6 faces. So has got a similar status. So half into 6 is basically give you 3. So 1 from the corner, 1 from the corner, and 3 from the face center position. Altogether, number of atoms will be number of atoms per unit cell will be 4. So we have seen that the number of atoms per unit cell in case of simple cubic is 1, and the number of atoms per unit cell in case of body centered cubic is 2, and the number of atoms per unit cell in case of face centered cubic crystal is 4. Okay, so you see the so far we have calculated the atomic radius. Atomic radius are equal to by 2 in case of simple cubic, and number of atoms is 1.
স্যার স্যার এফসিসির জন্য একটু আবার বলবেন ক্যালকুলেশনটা?
Okay, so keep. I'm going to explain this one later on. Remember this thing. Let me finish, and then we'll discuss. So number of atom per unit cell is 1 in this case. Number of atom per unit cell is 2 in case of horizontal cubic crystal, and number of atom is 4 in case of horizontal cubic crystal, and R equal to A by 2, root 3 A by 4 in this case, and then and root 2 A by 4 in this case. Now, what would be the immediate effect of these number of atom? Immediate effect of these will be on the density. Density of the material will be different. So now we're going to describe the find out the relationship between density and these lattice parameters. As you know, the mass of an atom, we can define the mass of an atom as atomic weight divided by the Avogadro's number. If you divide Ma by Na, it will be the mass of a single atom. Just now we have calculated the number of atom per unit cell. If we denote number of atom per unit cell by N, then mass of a unit cell will be N multiplied by Ma divided by Na, which is mass of an atom. So that will be the mass of a unit cell. Now, if the volume of the unit cell is V, and you know that density is mass per unit volume. If you multiply rho by V, that is also the mass of unit cell. So equation 1 and equation 2 actually represent the same thing. If 1 is equal to 2, from there you can calculate rho will be N Ma by Na multiplied by 1 by V. So we have studied cubic crystal system in detail. So B for cubic crystal system is basically A cube. So if I ask you to calculate density, then instead of V, you will use A cube, where A is the lattice parameter or lattice constant. Why this is called lattice constant? Like in case of cubic crystal system, A equal to B is equal to C, alpha equal to beta equal to gamma equal to 90 degree. So that means actually you need one parameter, A. If you know one parameter, then you know the unit cell. So that is why it is called lattice constant. So this is a very important relationship. You can calculate the theoretical density. This density is called a theoretical density. Theoretical density even before making the crystal. N is the number of atom per unit cell, which is 1 in case of simple cubic, 2 in case of horizontal cubic, 4 in case of face-centered cubic, and later on we are going to study hexagonal crystal structure, hexagonal close-packed crystal structure. That has got a number of atom per unit cell is 6. We're going to study this one later on. And then volume is A cube in case of, as I have mentioned, simple cubic, horizontal cubic, and also face-centered cubic crystal. Okay, so we are going to calculate theoretical density for typical example is chromium. So as we have mentioned earlier, the chromium metal is actually BCC. So in the exam, I might ask you, what is the crystalline nature of chromium? Answer is horizontal cubic. Draw a typical unit cell. So answer is very easy. You just draw the typical unit cell. So atoms will be located at the corner. Atoms will be located at the corner. And also in the horizontal position. That's the answer. And then atomic radius, atomic mass is 52. Atomic radius is 0.125 nanometer. And you know the number of atoms in case of horizontal cubic is 2. From this data, you are asked to calculate theoretical density. So atomic radius is given. So from atomic radius, we can calculate, previously we gave an expression R equal to root 3 A by 4. So A will be 4 or by root 3. From there, we can calculate A. Once we know A, density is N multiplied by MA by NA, because this number, and then multiplied by 1 by A cube. If you substitute the value of A here, you can calculate the theoretical density is this one, which is very close to the experimental density for a pure chromium metal. Okay, so if we look at this slide is very important. All the materials and their densities are shown in this figure. All classes of materials. First class is metals or metals, okay, or alloys. So you can find out the metals and alloys. Among the metal, look, magnesium has got this density is this one, and then aluminum, titanium, and on the top is platinum. Okay, look at here. If the density is higher, almost the material, the price is also very high. Okay, and over here, aluminum and magnesium has got almost very low density. That is why from the alloy of aluminum and magnesium is used to fabricate the body of the aeroplane and also high-speed train, because this become lighter. Okay, so that is called duralumin. You know that one. So you can design the materials. You required materials. You can design the required materials by making an alloy. Okay, from this data you can calculate. And then composites of okay, and then graphite or semiconductor ceramic. Graphite has got the lowest density. Graphite, carbon, all these are same. And then concrete. So that's very important for the civil engineer. Okay, and other materials. And these materials, although it shows in green, however, these are not the green materials. These are very harmful for our environment, and that was discovered lately. I mean, 2 or 3 decades or 4 decades ago, and we are using these very often in our daily life, like this PVC, and then low density polyethylene, high density polyethylene, and all those things. And their density is very less, and also they are very cheap. Okay, so due to that, we are using this one in large scale. However, they are making pollution to our environment. And then these are fibers. So wood or polymeric materials. Among them, wood has got the lowest density. That is why you see we use wood. Wood is actually renewable, and it is available in the nature, and also it is biodegradable. So that is why in our everyday life we use wood very much. Okay, and then some fibers are also used. So this slide is very important for if you want to make some new materials by alloying them. So this data is very important. And then some examples. So this will be homework. I hope you will be able to solve this problem by yourself. Let me discuss the example number 6. Niobium crystal is BCC, 47 cubic, and its density is 8.57. You know, the capital M is mega. Mega means 8.57 into 10 to the power 6 gram per meter cube, which is basically 8.57 into 10 to the power 3 kg per meter cube. It's same. Calculate center to center distance between the closest atom. So from this data, the density is given. So you might have noticed if you know the density, and then you can calculate A, lattice parameter, A B equal to A cube. So you can calculate, because if you know the density and if you know the crystal structure, you will, from the crystal structure you will determine N, and then from atomic weight you can determine the mass of an atomic weight. So only one unknown is there, you can calculate A. Okay, or in other words, if you know A and if you know the crystal structure, then you can calculate rho. Or if you know rho and A, by calculating N, you can find out the space that is as well. Like if you get in a cubic crystal system, if you get N equal to 1.975, that means which is almost 2, that means your crystal structure is bodycenter cubic. Sometimes you may get N equal to 4.221 to 3.5, less like that. In that case, crystal structure is space center cubic, and so on. Okay. So niobium is body center cubic, and you know the density, you can calculate A. So you can calculate A. Once you calculate A is called the edge dimension of the unit cell, because A is nothing but the edge dimension of the unit cell. Edge means this edge, or this one, or this one, this one. For cubic, all are same. So at first you will calculate B, A, and then calculate center to center with the closest one. As this is BCC, the nearest neighbor distance we have already calculated, which is root 3 A by 2. So once you know A, then you can calculate the nearest. And then here atomic radius is given, and it is copper, it is phase center cubic. From atomic radius you can calculate A. Once you know A, you can calculate density. And A is given, you can calculate the density. A is given, you can calculate the density. Very easy. And number 4 is, again, it is megagram per meter cube. So you can find out which is 1.5 gram per centimeter cube. And so density is given, you can find out the volume. Very easy. So you can calculate V in this case. And example 5 is titanium, BCC at high temperature, atomic radius is given. You can calculate how large is the edge of the unit cell. That means you will calculate A. And then once you know A, you can calculate the density. So we're gonna